For the chapter of light, you must understand these three aspects when we talk about light. So the three things that we tested would be reflection, refraction, and of course the combination of those two, total internal reflection. Let's start at reflection. Okay, so what should you remember? The key ideas for reflection would be about the properties of the image, right? So LVEU, right? You should remember what are these five properties. And of course, all these are for the image in a mirror. So what do I mean by understanding these five things? It means that for any question that involves a mirror reflection, you should be able to use these properties. Let's give you an example. Okay, if I'm talking about a mirror over here, and then there's an object here, and I say that this is my eye. Correct. So what we're so used to doing is, okay, I know how to draw the lens ray diagram. Sorry, not lens, a ray diagram. But the essence of the question is this: I would know where would the image be, correct? How would I know? Because here is my object, right? My image should be at an equal distance away from the mirror. And what we always do is that I'll draw the image. Okay, so I'll put a dotted like this, correct? And I should be able to see that this distance and this distance is the same. Oh, it's not the same. Okay, yeah, okay. But you can see, okay, not this part, but here. Okay, and then what you do next is that, oh, okay, same size, it's virtual. Can you see that? It's dotted, right? So it's virtual, same size as this one. Well, generally, I'm rushing a bit before you. You can't see laterally inverted. You can't really see upright in this case. But of course, if I use a different image like this, maybe if my image was something like this, right? Then, sorry, my object like that, then my image should be the same distance and then like that, correct? No, so, but then dotted. Right? Same size and dotted, right? And you see that, oh, equal distance away from the mirror, same size, and laterally inverted, left becomes right, right becomes left, and it's upright, equal size. See, all this all matters, right? The only part that you all would always do is this, that you will know how to draw the ray, right, from there, right? Something like this. Oh, sorry, this should be a bold line. So sorry, I'm so tired. Like this, correct? Now, this is basic. Because the next part that you must remember when I'm talking about reflection is that I know that there are laws to it. For example, not example, which are the incident angle is equals to reflected angle. Right? We actually can see it right here. Right? If I just look at one way, it would be something like this. I have my incident ray, and I must always draw my normal. Don't forget that. Always draw the normal. And this would be my reflected ray. Where are the angles? Always measure to the normal. Okay, incident angle, reflected angle. Please don't forget the normal. Remember that the angles which you measure always must be to the normal. Okay, okay. So what questions can I ask you for this? They may ask you, this is equals to that, is it? Or what if I tilt this by a certain amount? Then what is the angle? So sometimes they trick you by giving you this angle instead of this one, that kind of thing. What other questions could they ask you? Actually, generally, we'll be just asking about these few things. Okay, it only can be either a mirror with the ray here, a mirror like this with the object distance away, or it could be, the one I always tell you, right? There's a mirror here, there's a person there, there's an object behind you. So where is how far is the image of the object from you, that kind of thing, right? So things like this. All right, that's for reflection. What about refraction? Refraction, you must remember that the idea is that my light is not like bouncing, right? My light is bending. And refraction is about the bending of light. And light bends because of the idea of optical density, right? As I go to different mediums, especially when I enter through an angle, my light slows down or speeds up, depending, and after that it bends. So optical density tells you of my refractive index. What am I talking about? I'm talking about this formula over here, right? Every Every medium which my light can pass through has a certain refractive index. It tells you how slow the light is or how fast the light is inside there. Now, remember that the speed of light is always going to be 3 times 10 to the power of 8 meters per second, correct? Now, if I go into something else, another medium, I would have a different speed, right? Medium. So that's the idea, you see. This is speed of light, of light in vacuum. That is to say, right, that to find my optical density, either find sine I over sine R. Oh dear, I didn't write it properly, sine R. So sorry, guys. Or refractive index could be found by taking my speed in a vacuum over speed in a medium. Right? It's always faster, it's always bigger. This thing up here is always bigger, this down here is always smaller. The value of n should always be more than 1, because in vacuum, the refractive index is 1. There's no way that I can go faster than the speed of light. There's no way I can go faster than the speed of light. Nothing goes faster than the speed of light. But in another medium with a greater optical density, I would slow down. How does that look like? Not something like this. So this is my boundary between two mediums. Let's say air, glass. So let's say I have, oh dear, let's say I have a light ray coming here, right? Because refraction only happens when I enter in angle. So I have my normal. I always draw my normal. When does light bend? You must remember how it works. This over here will bend towards the normal. Okay, the way I taught you about how you see it bends using like either like a wheelchair or a car, how does the tires, like for here, right, there's 2 points, right? Here and here. Let's see, I'm just going to draw the car down here. Box. You imagine, right, there's 2 parts, right? This one over here, this part over here, it will enter here earlier than this other part, right? And if glass has a high optical density, that means I slow down. If this side slows down more than this side, then it will bend and turn this way. Okay, I talked about this many times in class. Please go back and refer to your notes. The angles which I'm concerned with always is measured to the normal. This is my incident angle, this is my refracted angle. Okay? Always remember that in my formula, up here, this thing up here, this is always the big angle. And down here, this is always the small angle. So I wrote 3 L's, small angle, right? That's why in class, I tend to write, instead of sine I over sine R, I tend to write sine big, the big angle, over sine small. Okay, and that works out. That works just fine. And you will see that, oh, in this case, see, this one is a big angle, this is a small angle, right? Why is this important to say it here now? It's because once I move on to total internal reflection, right, the whole idea of sine big over sine small is way more helpful. It's easier to use. Okay, now for refraction, what could they ask you? They could ask you calculation questions, right? Remember that this is the formula I'm looking for, correct? And this is the formula I'll use. So they must give you either n, this bigger angle, or the smaller angle, right? Because these are the variables. They'll just give you maybe 2 out of 3 of these things. So, for example, let's give you a tougher question, okay? Let's say this is glass, this is air. Okay, so glass. This would bend away from normal. Oh, sorry, let me do it again. Glass, air, correct? And then they ask you, they say this maybe, well, actually I have no idea. Maybe this is 55. Maybe this one over here is, I don't know, man. Let me try to use my calculator. Maybe this is 57. Here's my question. Ready? What's my refractive index? What is my refractive index? You know this angle, you know this angle. What's my refractive index? Now, I just gave you a really tricky question. You're going to use sine big over sine small. So which is the bigger angle? Are you thinking this is the bigger angle? Careful. Remember that we always measure our angles to the normal. As such, right, the angle that I'm interested in for this equation, for this formula, is actually 33. Can you see that? I hope you all could see how this is a very tricky question, because like I said before, it's always about where is the angle? Where is the angle? In this case, 57 is not the angle I'm concerned with. If I want to use sine I over sine R, or sine big over sine small, it must be to the normal. So hey, then I realize this is the big angle, this is a small angle, right? What do you get? Well, I'll get sine 55 degrees. Don't forget your sine, don't forget this degree over sine 33, right? It works out, right? Big over small. What do we get? I think, if I'm not wrong, what you will get is 1 point ish, around there, 1.50, I think. If I'm not wrong, that should be it. Okay, give that a try. Right? This is how they may ask you by giving you a wrong, in inverted commas, wrong angle. Or they give you like this, like they give you 33 and give you 55. They ask you to find this refractive index. So, oh wait, that's what the question is telling you. Okay, so that's for refraction. What else could they ask you? Generally, those kind of questions. Please do refer to your 10-year series that you have bought. You could take a look. Now, TIR, of course, is the big question which they always ask you. Let me show you a question which is possible. Okay, so this is from a question paper I set recently, not yours, but let's take a look at it, okay? In total internal reflection, maybe I explain before I give you the question, okay? In total internal reflection, I remember that there's a concept that I'm moving now, as far as I'm concerned, I'm moving from more optically dense to less optically dense medium, okay? So in this case, medium. It'd be like more optically dense would be something like glass. Something that's less optically dense could be like, air. So if I go from glass to air, that's going from more optically dense to less optically dense. But one more thing must happen though. For total internal reflection to occur, I need to consider the concept of critical angle. Okay, so to reiterate what this is about, I know that, right now, I'll just use this question to explain. Now, if I, yeah, going to this way instead. I know that if this is glass and this is air, I know that if I start at this angle over here, correct, something very small, is my normal, it will refract, it will bend away from the normal, right? Bend away, right? But you see, this is so big, right? What's the biggest this can bend? It will probably be when I'll just try increasing this one, make it bigger and bigger and bigger. But as I go bigger here, over here in glass, right, this will bend more and more and more and more until it reaches the maximum that it could possibly bend. It could possibly bend glass, right? So maybe like bigger here, and can we use green to make it more obvious here, right? The maximum it can bend, right, is 90 degrees. See that? So if I had to label this I, this is R, this is I, this is R, right? In this case over here, my angle R is 90 degrees. That's my maximum it can go. So now there's this angle, therefore, angle I. This is a special angle. This angle I is known as my critical angle, because at critical angle, what happens? When I am at critical angle, 准准 at that angle, my refraction would be 90 degrees. Okay? What happens once I get past this critical point, this critical angle? If I go beyond my critical angle, right? It's like the limit. Once I go past that limit, okay, once I'm bigger than the limit, just a little bit, just even by 0.1 degrees, I go past the limit. Well, nothing goes out anymore. No more refraction. Everything gets reflected back inside. You see that? Glass. Such that reflection now occurs, right? It's supposed to go through, right? Yeah, but in this case, because I'm at incident angle that's greater than critical angle, now reflection occurs, such that this is angle I, this is angle R, just like what we did for reflection. That's why TIR is a combination of reflection and refraction. So let's apply into this question, okay? So I'm going to end soon. Let's say for example, there's this setup whereby I'm at three different angles. At X, I'm telling you that this angle over here is less than critical angle. So what happens if my angle of incidence is less than critical angle? I can still refract, correct? Yep, I still can. So what would it be? Maybe it would be something like this. Okay, I refract. But once I'm at, so if y is equal to critical angle, if this incident angle is equal to critical angle, I know that critical angle means my refraction is going to be 90 degrees to the normal. So this one over here would be exactly along over here, such that this is 90 degrees. Here, see, now this incident angle is now greater than my critical angle, right? See, z is greater than critical angle. Then what happens? Well, if it's greater, I know that I cannot refract any further already. So what's it going to be equal to? I'm going to be like that, such that these two angles are going to be the same. Okay, this is what critical angle is. How do I use it? So let's say, okay, let's say that this angle here, angle y, let's say this is 42 degrees. What they can ask you is this: can you please tell me what is the refractive index of glass? Well, there's two ways of doing it, okay? I'm going to show you the long way, then the short way. The long way would be to use what I already learned over here. Can you see? Let's use the long way, okay? First. The short way, of course, you learn you use that first, but I just want to connect the ideas together. Okay, let's see over here. Which is my? I'm trying to look for critical. I'm trying to look for refractive index, correct? So n equals to sine big over sine small. Which one's my big angle? Is it this one or that one? This one 90, right? This one 42, right? So obviously this is my big angle, this is my small angle, right? Correct. Correct. So sine 90 degrees over sine 42 degrees. Okay. When you do that, well, sine 90 I know is equals to 1. Sine 42 is equal to angle. Sine 42 degrees. This should give you about 1.50, I think. Roughly that. Okay, try your calculator. Can you see that? Now, of course, this works very well, right? Because I see big and small. What you also would know in your notes and from class, the straightforward version, if I already know is about TIR, right? Sorry, if I already know it's about critical angle, I can just go straight. Sine C. And my C in this case is 42, right? See? Over sine 42. You get the same answer. So these are the questions whereby they ask you for refractive index. Okay. Generally, this is basically how the questions go. The different kind of questions is whereby they give you like maybe a prism. I think I've given you this before. So let's say I have a light. It goes like this, huh? Okay. Where does it bend? Where does it bend? How you know? How you know? Look at this. Remember to turn it, turn it. Once you turn it, you realize that oh, it actually looks like this. Can you see? Can you see this over here is what's over here? Just redrawn on this side. You can see very clearly where's my normal, right? It's here. Can you see? So likewise, I'll draw it over here. This usually is a step where a lot of students make mistakes because they don't realize this is this. So I suggest that you turn your page and put it in this orientation so you can see. Because in this orientation, you already know, right? If this is air, this is glass, you know what's going to bend. It's going to bend toward the normal, something like looks like this, correct? So over here, I'll draw the same thing, something that looks like this. Okay, you can see something looks like this. All right. Now, what if, what if, um, at this special angle, right, it turns out that over here, now this happens. Let's say, for example, okay, this happens. What's happening here? How come inside, then over here, how come it's along the surface? What's happening here? Oh, is this total internal reflection? No. This means that it's at critical angle. Why? Let me draw for you your normal, because this is 90 degrees, and this over here must be your critical angle. Okay? I'm not saying this will happen in your exams. Usually, this doesn't, right? Um, it's a more interesting question if it refracts or reflects, but you need to figure it out. How? Just go back and use the same concepts over here. Ask yourself, what's happening at this point? Is it this one, that one? Okay, and think for yourself, is this a critical angle? Where is the angle? Which one's my angle? Because it is very easy, let me zoom in for you, to forget which angle you're supposed to use. Okay, I'm going to use yellow color here. Some of you may think I'm supposed to use this angle here. This is going to be the wrong angle to use, because you must always measure to normal, between the ray and the normal. So this one. Okay, this is generally most of the things I can think of. And I think this video is long enough, 21 minutes, 22 minutes. All right, I hope this helps y'all a little bit more in your light. I think y'all can do it. Just try your best. Try to sleep earlier today also. Okay, hope this helps. Take care, guys.